The speaker is David Martí-Pete from University of Liverpool. And the title is on the computational complexity of Julia sets in the exponential family. Please go on.
Thank you. I would like to thank also the other organizers of the conference that invited me to give the talk, and then they asked me to become an organizer later. So today I'll be speaking about this joint work with Artem Dudko from INPAN that we started about a year ago when I was a postdoc there. So in complex dynamics, often when we want to understand the dynamics of a function, our first step probably is asking the computer to produce a picture for us. And then of course there is the question of how much of this picture that we get from the computer we can trust, how much we can rely that these computer generated pictures, they are accurate with respect to the real Julia set. So this is the topic of this talk. And so there has been a lot of work on the computability and computational complexity of Julia sets for the rational setting. But as far as we know, this is the first time that someone looked at the computability for the Julia set of transcendental functions. Okay, so in computability theory, what people do is they see whether, given a problem, the computer can solve this problem. If there is an algorithm to solve a given problem in an effective manner. And one of the pioneers of this theory was Alan Turing, who formalized this concept of an algorithm, right? He created this notion of a Turing machine, which is an abstract machine, which it has a finite number of rules, and you have an input, which is like a string of binary digits, say, and then either it produces some output or it keeps running forever, right? But for the purpose of this talk, whenever you see this concept of Turing machine, you can just think that I'm talking about an algorithm. So I will use the concept Turing machine and algorithm interchangeably for the purpose of this talk. Okay, so we say first that a real number is computable if there exists such Turing machine that, given a natural number, the Turing machine can produce an approximation of the real number alpha that is 2 to the power minus n close to alpha. So for arbitrarily small precision, the Turing machine can produce approximations of the number alpha. Of course, when n becomes larger, then the computer may take more and more time to produce these approximations, but nonetheless, we can get them. And for complex numbers, we have a similar definition. We just ask that the real part and the imaginary part are both computable numbers in the above sense. The easiest examples for computable numbers, perhaps they are these algebraic numbers, the roots of polynomials with integer coefficients. And we heard a few talks in this conference about several algorithms, including Newton's method, etc., to compute roots of polynomials. But so there are many more computable numbers than those. So basically, so for example, there are algorithms also to produce approximations of E and approximations of pi. And basically, every number that you can write down in a formula in an easy way, it turns out that it will be computable. So there are examples of non-computable numbers, but they are produced in a sense in an artificial manner. You need to do something special to end up having a non-computable number. For example, one way of producing them is using the so-called undecidable problems. And one such example is the halting problem. So this concerns whether, given a computer program, So it concerns whether there exists a problem. There exists a program that if you input a program in general and the starting condition for that program, in general, this program there is no problem that can tell whether the problem will run forever or it will finish in a finite time. So for example, you can use, if you want to create a non-computable number, you may define its digits by saying, giving a sequence of computer programs and starting conditions and saying it's 0 if the end program stops, and 1 if it doesn't stop. So it's this type of things. Everything else will be computable. But because Turing machines at the end, they have a finite number of rules. So it's something that you can input in the computer. So there are countably many Turing machines. Okay. So if we have a planar set, a subset of the complex plane, we can approximate it by using the set of dyadic numbers. Sorry if it's confusing. This is not the unit disk as before. It's the set of points in the complex plane whose real part and imaginary part are of this form. Okay. So then to describe a set S, we use this function that the variables are a natural number n and the point z that is of this form. So you should imagine this is like a square grid on the plane, and for every point z in the center of this square grid, this function will input a 1 if there is a point of our set that is at this distance, and 0 if there is no point of the set that is twice the distance. So here, note that there is an intermediate case, that this is not an exact description, so there is some inaccuracy for this type of thing. The picture that you should have in mind is something like that. So you can think that the dyadic numbers are the centers of these squares. So we color the square black, which is like this first case here. If there is a point on the set of the set that is inside this square, and then we color the square white if twice the distance there is no point. So for example, we color this square white if we know that all around here there is no point of the set. And then there is this intermediate case that if there is a point, here. So if there is a point not in the square, but in one of the squares nearby, then the computer program is allowed to color it black or white. Okay. So we say that a set is computable. Then if there exists a Turing machine that can produce this function h, or whether they can produce this square grid approximation with coloring the pixels black and white for all the dyadic points of this form. And this depends, T of n is the amount of time that it takes to produce the 2 to the minus n approximation of the set. So what are examples of computable sets? So if we take a polygon and we know that the vertices of the polygon are in computable points in the complex plane, then the polygon will be computable. But here I should point out that the notion of computability doesn't necessarily mean that the set is very complex or complicated in any way, because if you take this polygon and then you move it a little bit, the vertices of the polygon are in non-computable points in the plane, then automatically the polygon will be non-computable in this sense. Or similarly, if you take a disk, then you want the center of the disk and the radius of the disk to be computable points so that you can produce these approximations of the disk. So this is the example before. So does anybody want to know, anybody know or want to guess what is the, which set has this 2 to the power -1 approximation? Do you have any idea?
Sierpinski triangle?
That's a good guess, yes. But, so I was thinking, following Bishop's talk yesterday, where they appeared a lot of triangles and many of the domains were this triangle, I thought maybe people would suggest this one, but no, you're completely right. So this would be like a 2 when n equals 0, so 2 to the power 0 approximation. So this is pixels of side 1. So then if you increase the n, these are pixels of size 1/2 the side. This is 1/4, etc. Okay, so this is the final one. So what about Julia sets? So first of all, an important observation is that in order to look at the computability of the Julia set, we need to assume that we can compute the function itself, right? Because if you cannot even compute the function, then it doesn't make sense maybe to talk about the computability of the Julia set. So for this, we use this notion called oracle that we treat as a black box. So an oracle is just a type of function that can give us, it's like a black box that gives us the values of the function. So it's a function that, given a precision, we obtain a dyadic approximation of the values. So usually in the assumptions of the theorems, you will see that we are assuming that there is an oracle that can produce, in the case of the polynomials, for example, that can produce arbitrarily good approximations of the coefficients of the polynomial. And in our case, when we look at functions of the form lambda e to the z, you will see that we also require that we can get arbitrarily good values, arbitrarily good approximations of lambda, of the parameter lambda, because computing the exponential map is not a problem. The problem could be of the parameter. And note that this doesn't necessarily require that lambda is a computable number, because we are not assuming here that there is a single algorithm that can produce these approximations of lambda. We just assume that somehow we get these approximations. It may come from a Turing machine, or it may come from, I don't know, you may dream about them, I don't know. You just assume that this exists. So then we say that the Julia set is computable in time t of n if there is such Turing machine, such algorithm, that once you assume you can compute the values of f, then this algorithm computes the function h of s in time t of n, where s is the Julia set. So you produce these pixels, black and white, in a sense. Then this is said to be computable in polynomial time if the amount of time that it takes for the computer to produce the 2 to the minus n approximation can be bounded by a polynomial. So now in the next few slides, what we will do is go through several classes of rational functions for which it has been known that the Julia set is computable. So the first such examples are due to Braverman and Rettinger independently. So they first started looking at the class of polynomials, or more generally rational functions that are hyperbolic. So these are maps for which all the Fatou components are basins of attraction. And they prove that for each degree larger or equal than 2, there exists this Turing machine that if you assume that you can get the coefficients of the polynomial arbitrarily well, then if f is hyperbolic, then this algorithm can compute the Julia set in polynomial time. Okay, so you need to know that the function is hyperbolic and the degree of the map. So to prove this type of result, the proof is based on clever use of Coeve distortion theorem. So one reason I like this type of subject is because the statements of the results are in the languages of computer science, if you want this computability, but what is inside the proofs is pure complex analysis. So Coeve's distortion theorem plays a very important role in proving all this type of results. And the proof goes like this. Basically, you have your field in Julia set here, and you take a neighborhood U of the Julia set. So for example, you know that this will be contained in the disk of radius 2 for the quadratic family. And then there exists a positive constant C with the following property, that if you take a dyadic point Z, and then you iterate it, then you need to iterate it for this amount of points of C times n. So if you want an n 2 to the power minus n approximation, then you need to iterate C times n. And then at every step, you check whether your iterate will be still in your bounded set U that contains a field in Julia set. So if for all these iterates, the orbit of the point stays inside the neighborhood, then you can be sure that the distance of the starting point to the Julia set is smaller than 2 to the power minus n. While if during these iterations, the point has at some point escaped, then you can also deduce, you can also compute the distance in the following way. When the point escapes, then you can put a disk around this first point that escapes, such that you know that, because you have a rough idea of where the Julia set will be. So you can put a disk around this point that you know for sure that it intersects the Julia set, and then use Coeve distortion theorem to take pre-images of this disk along the orbit of the point until you reach the starting point. So you know that the starting point will have some given distance that you can estimate to the Julia set. This is how you prove this type of result. So a different, slightly more complicated case is the parabolic one. As you probably know, if you ever try to draw pictures of parabolic Julia set, it takes a lot of time for the iterates to escape from a small neighborhood of the parabolic point. So it's significantly slower to produce such pictures. But perhaps a bit surprisingly, Braverman was also able to show that for parabolic maps, you can still compute them. There is a Turing machine that computes the Julia set still in polynomial time. So if I understand correctly, there are two possible approaches how to do that. The proof of Braverman was like a direct proof. They just computed it and showed directly that they can do this in polynomial time. But more recently, Artem and David Suzanne made, there is a different paper that shows how to approximate Fatou coordinates. And you could potentially use this type of thing to also prove a similar result. So you can have these two approaches for the parabolic case. Then a third case that is also computable is when the field in Julia set has empty interior. So it's either, it could be like a dendrite, or it could be a Cantor set. And in this case, it is also computable. The type of algorithm that you would use in this case would be a combination of two things. First, you use an approximation from inside, say, of the field in Julia set. So you know that the repelling periodic points are dense in the Julia set, and they are easy to compute because they are roots of polynomials. So they are easy to compute. So you can first produce enough of these repelling periodic points. Then this would give, if you put a small disk around each of them, this would give you a neighborhood of your field in Julia set. And on the other hand, if you start with a disk that is large enough and you take preimages and preimages, you can see perhaps some of them here. You also know that these preimages, they will be eventually sufficiently close to the Julia set. So you just need to keep taking these preimages until your set is completely contained in this other neighborhood of the field in Julia set that you obtain from approximating the set of repelling periodic points. And at that point, you can be sure that your set will be a good enough approximation of your field in Julia set. So you may start thinking that everything is computable and everything is good, but that's not the case. So Braverman and Jampolsky also produced the first example of a Julia set that is not computable. So this might be confusing, and I'm sorry if it's so. So you're seeing here a picture of a Siegel disk. So for this particular one, probably it's computable. But what they proved is that there exists a quadratic polynomial that has a Siegel disk around the origin with the property that the Julia set is not computable. And you can also choose a rotation number of the Siegel disk to be a computable real number. And you can also choose it so that the Julia set is locally connected. Okay, so there are examples of quadratic Julia sets that are non-computable that come from parameters with a Siegel disk. Also, they showed this slightly different result that there are examples in the same type of class that they are computable, but the computational complexity is arbitrarily large. So it's not bounded like a polynomial, but it grows much faster than polynomially when n tends to infinity. So it takes longer and longer and longer to compute. And they were able to characterize also which cases are computable. They have this equivalence. So the Julia set is computable if and only if the inner radius, which is the Euclidean distance from the fixed point in the center of the Siegel disk, in this case 0, to the boundary of the Siegel disk. So you compute this distance. And then if this is a computable real number, you can be sure that then the Julia set will be computable as a set in the plane. Or equivalently, you can also check the conformal radius of the Siegel disk. So you take the Riemann map from the Siegel disk to the unit disk, and then you look at 1 over the derivative of this Riemann map at the center of the Siegel disk at 0. This is called the conformal radius. And in fact, it follows from Sbar's lemma and Koebe 1/4 theorem that the inner radius and the conformal radius, they are comparable quantities, but both of them imply that, that the Julia set of this function with a Siegel disk is computable. Okay, so moving on now to the work that Artem and I have been doing. So as I said before, there was no result about the computability of Julia set of transcendental functions so far. So we decided that a nice place to start is the classical exponential family with a parameter lambda between 0 and 1 and 1 over e. Also, let me remark that there is a considerable difference when iterating polynomials, say, and transcendental functions due to Picard's theorem, because when you're iterating a polynomial, once you enter a neighborhood of infinity, you know what will happen. You will continue escaping to infinity at the same rate. So it's more predictable. But when you want to plot the Julia set of a transcendental function and you iterate points and want to know whether the point escapes to infinity or not, this is much more tricky. And a priori, it is surprising that one could even do such thing, because as you know from Picard's theorem, it doesn't matter how close to infinity you are, that your next iterate can go everywhere in the plane with except one exception. So it is surprising that iterating your point only a finite number of times, you can actually predict in a sense whether the orbit will be escaping or not. Yeah, well, we're not actually predicting this, but you know what I mean. Like, it's in a sense surprising that we can produce pictures of Julia sets of transcendental functions in this accurate way that if you wanted, you could even use it for creating computer-assisted proofs or this type of thing. Okay, so we decided to start with exponential family. And as I said, we take the parameters first between 0 and 1 over e. This is the plot of the restriction to the real line. So at 1 over e, you have a parabolic fixed point. But then for smaller lambda, you have two fixed points you can see here. One of them in the left is attracting, and the one in the right is always repelling. And the Fatou set in this case is connected, and it corresponds to the basin of attraction of this attracting fixed point here. Okay. So it's very good to speak after Krzysztof because he already explained everything you need to know about these functions. So the Julia set of these maps, it's a Cantor bouquet. It's an uncountable collection of curves that join each of them a finite endpoint to infinity. And this set has, from the topological point of view, it's very interesting. It has several interesting properties, such as Karpinska's paradox, or the fact that if you take the endpoint union infinity, it's connected, but then you remove infinity and it's totally separated. Many, many nice properties. So we wanted to know whether there have been pictures of this Julia set, of course, for a long time. We're not the first to create, to produce algorithms to create these pictures. But what I think is we are the first in showing that these pictures that we get are actually, so they are computable. So it means that we can trust that these approximations that we will get from the computer using our algorithm that I will discuss in a bit are really accurate, meaning if the point is black, it means that within that certain distance, the size of the pixel, there is a point of the Julia set inside. And if it's white, then there is no point in twice around, etc. Okay, so how will we do this? So the Julia set, of course, is unbounded. So the first key step here is that your Julia set, which is, as I said, it's a complicated object, right? The magical thing happens here that if you want to obtain a 2 to the power minus n approximation of your Julia set, so you want to obtain a set that is at most this distance to the Julia set, then if you look far to the right, you can find some capital R, such that the intersection of the Julia set with this right half plane, actually there will be straight, the approximation, this intersection can be approximated by actually straight half the strips. Okay, so we define this set BR, which are these black. So here it's not obvious, but to the right of the red line, you're not seeing the Julia set of the function. You're seeing straight strips. And to the left of this line, you're seeing the Julia set. What is happening is that this, so when you fix an approximation that you want, you fix an n, then this n gives you an r, a value of r that depends linearly in n. So this function is like log 2 times n plus a constant that depends on lambda. I think it depends on log lambda, something like this. Such that to the right, these half bands are 2 to the power minus n approximation of the Julia set. Okay, so what do we know? So to the right of this line, we can use straight strips as an approximation. To the left of some vertical line, we know that there is no Julia set because it's the basin of attraction of the fixed point contains a left half plane. Okay, so to the left of such line, there is nothing. And we also know that the Julia set is 2 pi periodic. So at the end of the day, what we want to draw is whatever we want to test or find the Julia set within this square box that I'm kind of pointing at here. So we go from this potentially complicated problem of having an bounded Julia set to just reduce it to, we need to draw accurately this finite part of the plane, because the other one we know already. This is the same picture, but from the neighborhood of infinity. So here I put the half strips inside, and then I put the rest of the Julia set. And as you see, it kind of is obvious that it matches well. Okay. So how about drawing these things in this vertical band that I mentioned? We have these two types of results. Let me try to walk you through them. So first, we say that if you know that your orbit, the orbit of your point, stays to the right of some vertical line at m for the first k minus 1 iterates, and then it jumps to the left. So if the orbit stays around here for k iterates, and then it jumps to the left, then you can use this type of result from application of Cueva's theorem again to compute the distance. So you can compute the distance of your original point to the Julia set by using these quantities here. There exists this constant C1 and C2 such that this thing happens. Then what happens if you're iterating in this vertical strip, and then your point eventually maps to the right? Then you also have a similar type of result that says if you jump to the right, you also can approximate the distance to the starting point to the Julia set. Then the intermediate case is, so how long do I need to iterate, right? Because we only have a finite amount of time, say. So we need to make sure that the computer finishes. So we have this type of result that says, okay, if you are in this type of vertical band and you iterate, so for every n that you want, there is a function capital N that tells you if you iterate at most capital N of n, sorry, too many n's maybe, capital N of n times, and you are still within this band, so you have not fallen in any of the two cases I discussed before, so you have not gone to the left of this vertical line at M, and you have not gone to the right of this other vertical line at R. So if you're still within this band for all these capital N iterates, then you automatically know that the distance to the Julia set is also bounded by 2 to the power minus n. So it's a bit similar to what happened in the hyperbolic case before, right? If you are not in the Julia set, so if you, in the polynomial case, when you are outside the field in Julia set and you iterate a lot and you still have not left the neighborhood, the more you iterate, it means the closer you were originally from the Julia set, because it took more time for you to escape. Okay. So don't get. So I just wanted to show a picture of how the algorithm for doing these pictures in the way we do it would work. I'll just describe some things quickly. I'm not going to go into detail too much. Basically, all I want to mention is we can compute all the parameters. So we have formulas for all the parameters involved in this easy case of lambda between 0 and 1 over e. So then what we do is we obtain dyadic approximations of the orbit of the point and also of the derivative at the orbit of the point. This can be computed recursively from the previous ones. Okay. Then we check whether you go outside to the left of some line, and yeah, or if you go to the right of some other line, and then you can, the output of the program is returns 1 if this dyadic point of level n is at a distance smaller than 2 to the minus n to the Julia set, and 0 otherwise. So either you color this pixel black or white. So this is how it would look. We have not yet implemented this algorithm, but this is an algorithm that can draw an arbitrarily good approximation of those Julia sets that I was mentioning. Okay. So as we have seen in Krzysztof talk before, when you have a hyperbolic map in the exponential family, there are two cases. Either the period is 1 and then the Fatou set is connected and the Julia set is a Cantor bouquet, or if the orbit of the periodic attracting point has period strictly larger than 1, then in this case the Julia set, then the Fatou set will be disconnected first, which implies that there are infinitely many components, and the Julia set is in this case a pinch Cantor bouquet. So you have the Cantor bouquet and you have some rule that identifies some of the endpoints of this Cantor bouquet, infinitely many of these endpoints. So it becomes a bit more complicated. But in either of the cases, so the first cases of lambda between 0 and 1 over E, they are all in the first category. But nonetheless, we have this result that says that if you have a map in the exponential family with an attracting periodic cycle, whatever parameter it is, then there is a Turing machine that uses an oracle for the value of the parameter lambda, so that the Julia set is computable in polynomial time for any hyperbolic map in the exponential family. How do these maps look? I must confess, I stole this picture from Krzysztof, Bogusza, and Anna's paper. So to the left, you have a real picture. I mean, it's again not generated by our algorithm yet, but a bit more colorful, say. And to the right is the sketch of how this looks. So I just want to say, so there is, so let's check it carefully. So here we have a 3 periodic orbit. They are these black points, 1, 2, and 3. Then we have in red here the asymptotic value at 0. For the exponential family, if you express it the form lambda to the z, the asymptotic value, which is the only singular value, will always be at 0. Then what we did here is, you can see here some small disk that contains the attracting periodic point and the asymptotic value. Okay, so we take this small disk here, and we take the first preimage, which is this dark purple domain here that contains a left half plane and contains, of course, the other periodic point. Then if you take a further preimage of this, you obtain this dark orange set here. Okay. And then one more, and you return to this type of lighter green domain here that contains the starting disk and goes to plus infinity along the real part to plus infinity. And then if you do one more step, which would be the corresponding one to go to all this domain here that you see, like the blue plus the white that goes in these channels to plus infinity, then this would be this other lighter purple. Can you see? So this darker purple corresponds to the light blue, and this a bit lighter purple here corresponds to white here. So you can see that it gets inside here, and then the other part gets inside here as well. Also, let me point out one observation that I said that for P strictly larger than 1, we have this pinch Cantor bouquet, which is quite different from Cantor bouquet in general, but here it is already obvious that if you look far enough to the right, then again your Julia set will look like just half strips. You don't see all this complication, which is the main reason I would say why our algorithm works. That we don't need to worry about the detail close to infinity, because there we already know what the approximation will be. So we only need to care about this bounded part of the plane. Okay, that's all I wanted to say for today's talk. So I just thank you for your attention and wait for any questions. Thank you.